Cool. So I think we're starting with proposition 34 today, and this is going to be the first time we meet parallelograms. So let me just write down the statement. Okay. So um, I'm not. I don't remember whether we defined what a parallelogram is from last time, but I guess
think so.
yeah. So maybe I don't think he does in his text either. Um, so maybe we'll just well, I'll do the proposition, and then maybe in the middle we'll you know, give a definition. So the the opposite sides and angles of a parallelogram. Oh, I need to take my jacket off because last time it caused problems. I think both audio problems as well as blackboard problems. Okay, so where were we? Of parallelogram are equal, and that any diagonal cuts the parallelogram into two equal halves. Into two equal. I'm gonna just say two equal triangles, and actually I'm gonna specify congruent. We're gonna meet another notion of equality a little bit later on, so I think this is my excuse for using modern terminology. Triangles. Okay, so I guess if you look at the statement, the opposite sides and angles of a parallelogram are equal. I guess the definition we want to take is that a parallelogram is just the intersection of two sets of parallel lines, right? Because we're not saying anything in the definition about equality of sides or angles, right? That's coming from this definition. So you know, if that can't be the definition, so it must be that we're using intersection of two sets of parallel lines as a definition of a parallelogram. Okay, so let me draw the diagram here. So the assumption is that we have a figure like this, a quadrilateral like this, and the opposite sides are parallel, right? I'm going to label it A, B, C, D, C and D. And I guess the claim here is that the opposite sides and angles are equal. So in fact, the statement here, both, or actually all three of these statements are going to follow if we can show that the triangles, you know, did I forget to use the line tool? Sorry, I guess we're going to have a wonky parallelogram today. We're going to cut the parallelogram in half like this. And the claim is that the triangles are ABC and DCB are equal. Okay, so so this obviously is what this last statement says, right? Any diagonal cuts the parallelogram into two equal congruent triangles. In fact, we only have to do this for one side. The other, you know, the other diagonal will be exactly the same proof. And if we prove this, we'll also have the fact that opposite sides and angles are going to be equal, right? If these two triangles are exactly the same, congruent, equal, whatever you want to call it, then the first two statements will follow as well. So next board, proof. So the next board, the proof is it's just going to be a simple application of proposition 1.29. So proposition 1.29, right? And 1.29 is talking about alternating angles, right? If for those of us who don't remember, so basically it says that if you have parallel lines, two lines, and the line cutting it, and the line here will be BC, cutting the parallel lines A, B, and C, D, that the alternating angles formed from such a configuration are going to be equal. So the pairs of alternating angles and the alternating angles are going to be ABC, and so there's a first pair BCD on the parallel lines the parallel lines AB and, well, AC actually, AC and BD are equal. And similarly, the same kind of, exactly the same argument, the alternating angles ACB and CBD are also equal. So I'm actually going to hop back to the diagram and just mark them in here like this, right? These two angles. Just I wasn't intending on using red. I was going to use, maybe I'll use orange, right? These two are going to be equal. And so, by proposition 26, the triangles ABC and DCB are equal. Okay, so therefore, that is AC is equal to BD, AB is equal to CD, so these are opposite sides, and the angle BAC is equal to angle BDC. And so we also have, right, ACD is equal to ABD, since they are sums of equal angles. This is probably not the best way to say this. But if you go back to the diagram, right, what we're saying here is that, well, you've got these two triangles, they're congruent, right? The orange, well, ACD and ABD, they're both sums of the orange angle and the green angle, so they must be equal. CAB and CDB, well, they're angles of equal triangles, so they're also equal as well. So that does it. Now, this is a little bit different from how Euclid presented it in the text. In the text, Euclid gives an additional argument using proposition 4 that ABC and DCB are equal using the another test for congruent triangles, and the test here is two angles and the included, or two sides and the included angle. And I think the reason why he does that is because proposition 1.4 in the statement actually explicitly says that if these conditions hold, right, two sides and the included angle are equal, then the triangles are equal, right? In proposition 1.26, there's no explicit statement that the triangles are equal, but in the proof, that actually is what is shown. So I think the argument given here is sufficient. We don't have to belabor the point and repeat basically the same argument to show that the triangles are equal. So I'm going to end it here and say that argument covers all three of the statements in proposition 34.
Yeah, I thought that was weird too, that in proposition 26 he doesn't actually say they're equal. I don't know why. It's kind of a little strange.
Yeah, I think, I mean, I thought maybe I missed something, but at least in the case where you've got two angles and the included side, right, that's that the proof, if you go to that does show that the angles, the triangles are the same. If you've got like two angles on the side that's not included, maybe you can flip it, right?
Yeah, but the point of equality is, I mean, by equality always means you can apply.
Right, yeah,
Oh,
yeah.
I see.
So it's
You're
not like,
asking, yeah, whether you can use O2 or SO2
right,
for
that's the
translation.
difference. Yeah.
Interesting. I hadn't thought about that. Okay.
Is
Yeah,
there
I'll
is
have
there
to
is
think
there an
about it.
O2 going on here? Like, do we can we flip it in 1.26? I didn't look at it as carefully because that's the other case that we're not using.
Yeah, is the notion of equality just rotations and translations, or are you
Right.
also allowed to reflect in a line? Yeah, this is an interesting point. Yeah, I wanted to riff on this a bit in the proof of proposition 35 as well.
Cool.
So yeah, maybe let's get on with that.
All right.
I guess I'll attach a speaker. Yeah.
Yeah.
Okay, so proposition 35 is about equality of parallelograms. It says parallelograms which are on the same base and in the same parallels, because these 3 pages are full of new terminology, in the same parallels, one of them being the base, I guess it'll be clear in the picture, in the same parallels are equal to one another. And I think it's fair to ask what Euclid means by equal. Let's just review briefly. So we have equality of line segments. Equality of infinite lines is never discussed. You might say they're parallel. That's the notion of equality of infinite lines. I'm not sure, but that wouldn't be consistent with what you say about finite lines. But finite lines are equal if they're the same length. Not that length exists as an independent concept in Euclid, right? There's simply equality of line segments. And what he means by that implicitly is related by what we call the Euclidean group. That is, you're allowed to rotate and translate a line segment and get it to perfectly overlap with another one, and then they're equal. And he has the same notion for triangles. He simply says they're equal, but what he means is that you can move them around and put them on top of each other and they become the same. What Kenneth and I nearly called you Euclid, Kenneth. What Ken and I were discussing a moment ago was when you just talk about equality of triangles, whether you're allowed to, are those two equal? They're equal because I can reflect in this line. I think Euclid certainly intends that. He uses that. I think we'd have to go back and find the first occurrence of how that's used. So the notion of equality of triangles has to be that you're allowed to move them around, you're allowed to rotate them, and you're allowed to reflect them in a line, which generates a group that we know as the Euclidean group in the plane. I thought that was because of Euclidean, sort of just because the Euclidean plane and it's the symmetries of the Euclidean plane, but I guess the terminology must arise from the fact that it's the group of symmetries that Euclid uses. Okay, so that leaves, however, the question of, well, what about parallelograms? Well, the obvious answer is you're allowed to do exactly what I just said for triangles. That's enough discussion. Let's get on with the proof. So let ABCD and EBCF be parallelograms. On the same base BC. So this picture actually leads you to ignore a special case. I'll comment, well, not a special case, half of the cases, but I'll ignore that and come back to it. Okay, so here are the two parallelograms on the same base. So the base, I'll draw it in a moment, is BC. And then off that, I've got these two parallelograms. So that's AD, and that's EF. Yep. And to say in the same parallels is, well, they have the same base, BC, and I'm assuming AF is on a line, right? So that this line is the same parallels. So that's the part of the hypothesis. Okay. We claim ABCD is equal to EBCF. I'm not going to define equality until the end of the proof. It will emerge what notion of equality I'm using, okay? Okay, so here goes. Since ABCD is a parallelogram, we have AD equal to BC by what Ken just did. So maybe I'll indicate that. AD is equal to BC. But then by the same argument, BC is equal to EF, right? So by common notion, whatever it is, 1, I suppose, AD is equal to EF. And here's the part where it matters. So the way I drew it, of course, there's no reason this couldn't have actually been to the left of D on the line AF, right? So this is sort of half the cases, well, whatever, there's no sense in which it's half. This is one of the cases, as in the picture. I'll leave the other case sort of as an exercise because it follows from the same arguments. So let's stick with this case where E is to the right of D. So there's no, that is the point of overlap here, which is called G, sort of actually exists. The line BE and the line CD meet inside the figures, so to speak. All right. And adding DE to both, that is to AD and to EF, so that is I join this line here. So since AD is equal to EF, AD together with DE, that is AE, must be equal to EF together with DE, that is DF. So now the trick is to compare this triangle and this triangle. And we see, in fact, that they're the same. Actually, this proof is pretty cool, I think. Okay. Also, AB is equal to DC. That's by proposition 34 again. So now let's think about these triangles. We have side equals side, we have side equals side, and we just need one of the angles to agree. But these angles here are, what's that? Exterior and interior angles of parallel lines, sort of intersected with a line. So let's say that. The two sides EA, AB equal the two sides FD, DC. And the angle FDC equals DAB, and that's by proposition 29. So that's using the fact that FDC is an exterior and DAB, the interior angle of this sort of arrangement here. Right? That's proposition 29. Therefore, the base, right? So I've now shown these two triangles are congruent. So the base, which is in the one case BE, equals the base, which in the other case is CF. Yeah, all right. And the triangles EAB is equal to FDC. So this is proposition 4, which we just mentioned. Okay, so I'm almost done. I'll have to go over to the next board, but so maybe I'll just quickly reproduce that. So those two triangles are the same. And then we have this other little triangle in common, DGF. Right? So I've shown that this is BC. A, D, E, G, F. So EAB equals, and here it gets interesting, FDC. Let DGE be subtracted from each. I have no idea what that operation is. What does it even mean? I mean, it's clear what it's supposed to mean, right? In some sense, informally, here's DGE. So I've got these two triangles. They're equal. If I subtract this from both, then the remaining things are equal. We invent a new name for those. That's a trapezium. So what we discover here is that, I guess it's common notion 3. Let me just double check, which says if you subtract equal things from equal things, the remainders are equal. Right. Common notion 3 says if equals be subtracted from equals, the remainders are equal. But what we discover here is that this common notion applies not only to lines, we've used that before, but also to shapes. And even if the result is not a shape we've considered before. Right? So this is, I think this is actually a pretty big conceptual step here buried in this proof. You could just say, well, what we're saying is the areas are the same, right? But there isn't in Euclid a sort of notion of area independent of, like, there's no way of saying that the things have two area if they're not the same shape, in the sense that they can be related by transformations. There's not an independent notion of area measured by a number. That's not something that exists. So all that this can possibly mean is that these shapes, A, B, G, D, equals the trapezium, which is just the word for the shape we just made, EGCF. And what we have to mean by that is that you can, well, the same transformation, this is my interpretation of this equals, some transformation can be used to put those two triangles on top of each other, right? In this case, just a translation will do. That same translation, if you execute it on the shapes obtained by deleting that triangle, well, they don't actually put the figures on top of each other anymore, right? So what does this equals mean? Right, because we deleted it from other corners. So I'll keep going, but I'll leave that as something to think about. Okay, so the trapezium ABGD equals the trapezium EGCF. Note that he's kind of careful to elaborate that in the correct order. It now matters, right? ABGD is equal to EGCF. You could reverse the order of those letters, I suppose. Okay, anyway, we're sort of done with the proof. I'll stop prevaricating about it. So let the triangle GBC be added to each. All right, so we know, whoops. Let's get rid of this stuff. So we know this trapezium equals that trapezium in some sense. And so if I add to both a triangle, then the shapes I get by doing that will be equal. That's common notion 2. Right. This shows the parallelograms ABCD, which is obtained by adding this to this, and the parallelogram EFBC, which is obtained by adding that to that, have to be equal. Which is what we wanted to show. Now, I don't mean that they're literally on top of each other in the sense that E is equal to A, right? Just that the two shapes are related by some transformation. Exactly what transformation you're supposed to use here, it's actually not completely straightforward, right? Because of the way that this was subtracted from different sides of the triangles. So I'll leave it at that, but we can talk about it a bit more. You have any comments on that, Ken?
Yeah, so I just thought about it a little bit. In the previous proposition 34, I think, yeah, the O2 is probably the right transformation group to use, right? Because even in proposition 4, whatever it is, where you have two sides and the included angle being the same, right? Those triangles could be reflections of each other, right? And they'll still be equal.
Right.
Yeah, so I don't see a reason why proposition 26 didn't just go out and claim that the two triangles, are equal with the hypothesis that two angles in the side are equal. So I'm safe in invoking that proposition. But yeah, I think here
Yeah.
also you have to you're reflecting, right? So you can't just rotate one of the trapeziums into the other by construction, right?
Yeah, actually, I'm a little confused about this, if I'm completely honest. So we know this angle is equal to this angle.
Yeah.
We know that is equal to that for the same reason. But is it actually clear that, I mean, the way I've drawn it, it looks like you can reflect it, but
it may actually not even be, is that right? No,
it certainly seems to say the areas are the same, but is it actually the case that there's a transformation I can deduce?
maybe not actually, because you can draw the F. If you drag that F out, oh no, if you drag that F out, E comes with it, right? Yeah, I don't know.
Oh, that was a question I had too. Like, are you allowed to shift EF?
Yeah.
I mean, all I'm given, so I can draw that as far out as I want in the setup for the problem, right? So, but do you mean some other notion of
does this work too?
Yeah, this is fine. Yeah, the special case I was referring to that you need to consider separately is nobody says you didn't do this. In which case there is no G. It's fine. You just don't. I worried about that this morning. You just don't have the step where you delete D, E, G. You just add in B. I mean, you add in this trapezium to this parallelogram. Sorry, trapezium to both. But yeah, it's otherwise the same argument. But you do have to deal with this slightly differently. Yeah.
So does Euclid assume, like those two parallelograms on the left that you just drew, does Euclid assume that those have the same area?
Well, that's what he seems to show. But my question is he actually showing they have the same area, or that they're equal in the sense that they're related by a transformation, so rotation, translation, and reflection?
Oh, gotcha.
what we seem to have shown unambiguously is they have the same area, whatever that means, right? I mean, like, apparently to show the same area at least has to include the notion of chopping them up into bits by lines and reassembling the bits. And if the bits somehow are equal by some other notion, for example, the way triangles are equal by symmetry transformations, then you count the resulting thing as having the same area. We haven't discussed any of that, of course, but that seems to be implicit here. But maybe I'm just a bit dense, and actually there is a transformation. I mean, it looks like it in the picture, but I'll have to think about it.
If you draw a rectangle and then draw a parallelogram on the side, then there's definitely no transformation, right? Like you just have a right angle starting with A, B, C, D is a rectangle.
Right, right.
And you can't, right? In general.
Yeah. Good. Yeah.
That's way too nice, Dan.
Yeah. This definitely we're fooled by the diagram in this case, right? So what Kenneth is saying is draw one of them like this, and then one of them way out here, and yeah, those are not the same thing. Right, good point. So what we actually showed was they have the same area, whatever that means. But then this word equals is like super scary, right? Because we have a notion of equals for lines, for triangles, and now for parallelograms. But for parallelograms, it's something completely different.
Yeah, we're going to have to be careful with the language, right? Sometimes when I'm reading Euclid, I'm like, what do you mean by equal? Even before this, right?
That's interesting, though. I think this is as I said in the Discord, this proposition is kind of wild. Like a lot of stuff happened here. Okay, thanks everyone. We'll leave it at that for Euclid.